Okay, in this video, we're going to talk about modeling with exponential decay. Okay, so radioactive material decays exponentially. The amount of material at time t is given by A equals A0 e to the negative kt, where k is a positive constant, and in fact k is equal to ln2 divided by h. Now what is h? H is the half-life. So we had a similar formula when we had exponential growth. In exponential growth, it's not, you have almost the same thing, except there's no negative here. So exponential growth is growing, this is decaying. And here's A0, and what happens is that after a period of time, a fixed period of time, which is h, you're going to get half of the material that you had before. And then another fixed amount of time, you'll have half the material again. In base 2, which I think is easier to understand, you're going to get A equals A0 e to, sorry, not e, because we're doing base 2 to the negative t over h. And what this is going from base 2 to base e, we're getting a change of base formula. And so, see, in base 2, you could look at it this way. So here we have t, and then we'll have a. And so suppose you start off at time 0, then you're going to get a0 2 to the negative 0 over h, which is just h0, because 2 to the 0 is 1. But then if you have time h, we're going to get a0 2 to the negative h over h, and so that makes a0 2 to the minus 1, which makes a0 over 2, so it's half. And then at 2h, you plug that in there, and you're going to get a0 2 to the negative 2h over h, and this makes a0 2 to the minus 2, which makes a0 over 4. So if you use base 2, it's easier to understand what's going on, but we don't use base 2 for reasons that have to do with calculus. So we just don't do that. So if you start off with a0 over here at time 0, and then at h, you're going to get half of that. And then at 2h, you're going to get a fourth of that. So it exponentially decays, and then if you have 3h, you're going to get 1/8, and so it just keeps getting smaller and smaller by multiplying by 1/2. So why not stick with this base 2? There's reasons in calculus we want base e. When we go from this equation, let me write it again because it looks messy there. Oh, but I made it messy again. Oh, gosh. Okay, so anyway, so when you use base 2, you have this equation here. You can go to base e by a change of base formula, and we get this equation, which could be written also as a equals a0, and I can replace k by this ln 2 over h. but this is good too. Okay, so let's go ahead and do an example. All right, so we're going to look at carbon dating. So the idea is that everything that's living has some carbon in it, and some of the carbon is an isotope. So carbon usually has 7 protons and 7 neutrons, and so it has an atomic weight of 12. Carbon-14 has an atomic weight of 14. So this is the cycle of life. So here is, say, some plants. Okay, I don't know. These are plants. And then what's going to happen is it's going to make cloth. And then what's going to happen is that a person's going to wear that cloth, like maybe an important person, like a pharaoh or someone very important. So I put an important hat on them. So they have this hat on, and then what happens to them? Our bodies are all, for everybody on Earth, our bodies will die. And so there they go, and they're put inside a tomb or something like that. And then archaeologists excavate. They measure the carbon-14. And what they do is they look to see how much carbon-14 is left, or how much there is. So they look at how much C14, which is carbon-14, remains. Now, the half-life of carbon-14 is 5,730 years. So what this means is that however much there was, like say there was 1 unit of this carbon-14 5,730 years ago, now there's half of it. So this person maybe is an Egyptian important person. The plant is made into cloth. The cloth is made into this tunic. The person dies. If they died 5,730 years ago, if they look at the cloth, then maybe it's not a mummy or something, but anyway, if you look at the cloth, half of the carbon-14 should be gone. And so what they do is they excavate and they look at the cloth. They might take a small sample and they measure how much carbon-14 is there, and they say, well, they have an understanding or somehow of knowing how much carbon-14 was there 5,000-6,000 years ago, and so then they can make their estimate that way. So okay, so the exponential decay function is a equals a0 e to the negative kt, where k is equal to ln 2 over h, and for us, h is 5,730 for carbon-14. So a new cotton shirt contains carbon 14. How much carbon 14 will there be after 3,000 years? Sort of a long time. Assume A0 is equal to 1. So what we're looking at is not how much, but what percent. So actually I should say what percent. Okay, so we're going to use our model here where I have A equals A0 e to the negative kt. And I'm going to put in that A0 is equal to 1. I'm going to look at K is equal to ln 2 over h. So that's going to be, well, and then h is 5,730. And then I'm letting t equal 3,000. And then we're just going to, just put everything in there and calculate. Okay. All right, so I have that, and I'm just going to go with it. Okay, so A equals 1, e to the negative, and then K is ln 2 over h, but that's 5,730. And then T is 3,000. And so now it's just up to me to get this by putting this in the calculator. This is the answer. It's just simply that that sort of doesn't really make it have a lot of meaning for me right now because I have to figure out what that number is somehow. Or anyway, I'm gonna use my calculator, and then as I do that, I would say there's a possibility I'll get that wrong, but because I might put the wrong number in the calculator. I mean, that's no excuse, but I have a whole bunch of stuff I could talk about with calculators. So okay, it's possibly going to work. So I'm getting this is equal to 0.695653, etc. So this is around 70%. So after 3,000 years, around 70% of that cotton is left over. Now let's do part B. If a piece of cloth found in a tomb has 60% carbon 14 remaining, well, then how old is the cloth? Okay, so our solution is that we are going to use A equals A0 e to the negative kt. K equals ln 2 over h. But that means the K is equal to ln 2 over 5,730. That is the half-life for carbon 14. And then we're also going to use that A0 is equal to 1. No, is that what we're going to do? No. Oh, actually, yes, we are. We're going to say that A0 is equal to 1, and that A is 60% of 1, and 60% of 1 is 6. It'll turn out exactly the same if you say, well, let A0 equal 100, and then 60% of 100 is 60. So it'll work the same way. So if I have 0.6, which is 60% of 1, e to the negative ln 2 over 5730 times t, and we're going to try to find t. Okay, so let me go over this again with an a0, how I pick that. I could pick any number, like say I pick 100, but the a should be 60% of that. So if I have 100 over here and 60 over here, I would divide both sides by 100. And I'd get 60 over 100, which is 0.6. So I'd end up with the same place anyway. And then what we're going to do is we're going to apply ln. That's how we solve exponential equations when you have a t up here. So we have ln of 0.6 equals ln e to the negative ln 2 5730 t. Those cancel out, and I mean the ln and e cancel out. And sort of almost there. And then we multiply both sides by the reciprocal of this fraction. So I'm going to get negative 5730 divided by ln 2 times ln of 0.6. Now the thing is that, okay, logarithm has domain all t greater than 0, but an ln of 1 is 0. But ln 0.6 is a negative number. So see, t should be positive. But it looks negative because I have negative here, but ln 0.6 is also negative. So anyway, you can really see it if you use a calculator. And hopefully I got that right. And so this is 4222.8128, etc. And so this is t is around 4,223 years old. So that's how old this cloth is. There's other materials or elements where you can apply the exponential decay and you use it for dating how old something is. But carbon is a really well-known one. All right.